Okay, this is going to be our first lecture for Chapter 6, which is Thermochemistry and Thermodynamics. But before we get into that, let's do a little bit of review. So we have four most common gases in the atmosphere as being nitrogen, oxygen, argon, and carbon dioxide. And so we're trying to figure out which one has the highest average kinetic energy at room temperature. So they're all moving around. We're measuring the temperature. They all have the same temperature. Which one's got the highest average kinetic energy? It's a nitrogen, oxygen, argon, and carbon dioxide. And remember, since they're all at the same temperature, then they all have the same average kinetic energy. Their velocities are different, but their energy is the same, so that should be the same. Now, if we're looking at which of them will have the greatest root mean square velocity, so that's their velocity moving forward at the same temperature, 300 Kelvin, now we need to figure out their difference. So we should look at our molar masses. Nitrogen is 28, oxygen is 32, CO2 is 32 plus 12, so 44. SO2 is 32 plus sulfurs, which is another 32. And so that brings us up to 64. And so remember, if they all have the same kinetic energy, then the smaller item has to be moving faster. And so our greatest root mean square velocity should be our nitrogen because it's got the lowest molar mass. So lowest molar mass means that its mass is less, so it has to be moving faster to have the same kinetic energy. The rate of a fusion is 4 times the rate of B, which best describes the ratio of their molar masses. So remember that the rate of a fusion, what it comes down to is the gas 1's rate over gas 2, right? So that ratio is the square root of the molar masses of 2 divided by the molar mass of 1. And so the idea behind it is that our second gas, if it's heavier, it's going to have a higher molar mass, so that should go on top. Whatever is lighter should have the faster rate. And so that's why they're inversely related. So this is where we kind of see some mistakes that happen is when people are using this equation, is that we forget to put the gas 1 and its molar mass down at the bottom. Here we use 2 m's to do molar mass. So this is telling us that the ratio of the fusion is 4 times the rate of B. So that's A to B, so that's 4 over 1. So the square root of them is going to be the molar mass of 2 over the molar mass of 1. So 4, we have to get rid of that square root sign, we square it, so 16 is molar mass of 2 over molar mass of 1. So that tells us that the molar mass of B should be 16 times that of the molar mass of 1. So that should be the molar mass of B is 16 times that of the molar mass A. Okay. And so now that we have a little bit better understanding of what's going on with our gases, we're going to start to look at the energy of our systems. And so energy is a little bit different than matter. Matter is all of the physical materials that we have. But energy affects that matter. It affects how much of those reactions we can do because there's a requirement of energy for us to do some of these processes. So energy is anything that has the capacity to do work. And if we think about what work is us making a force over some distance. So our energy is kind of like our force times distance, which is our work. Now, heat is another type of energy, and heat is the flow of energy, and it's specifically caused by a difference in temperature. And so energy gets exchanged through the contact of objects. So the particles can collide, they can exchange energy. The materials can be touching each other and they can exchange that heat. So you can kind of think of energy as a quantity an object possesses or as a collection of objects possesses. And heat and work are two different ways where we can exchange that energy from one object to another. So we can either put heat inside of an object, or we can put work inside, or we can have heat, energy be removed through heat or work. And so we're going to further classify that. So our energy can be spread into some smaller categories. We have kinetic energy, which we've kind of been talking about just this morning, is the energy of motion or energy that is being transferred. Whereas thermal energy is kind of associated with our temperature. So thermal energy is a form of kinetic energy because kinetic energy is measured by our temperature. So you can kind of see that we have this category here. This is the energy that we have related to it being in motion or the energy associated with being in heat. The other side is what we call potential energy or it's chemical energy. So potential energy is kind of energy that's stored in an object and it's associated with what it's made of or the position of its object. So if you have something that is big and heavy and it's stored up high, it has potential energy stored inside of it. Because at any moment, it could be dropped and that potential energy can then be converted into kinetic energy. It's like all of that energy that it took to push that boulder up a hill, that energy is now being stored inside that boulder at the top. And so when that boulder rolls down that hill, then that potential energy is being converted into kinetic. For chemistry, that potential energy can take on another one. It's called the chemical potential energy. And it's because of the relationship of the atoms inside of those molecules together. And so when molecules are formed, there's an energy that can either be released or stored or converted as we make these bonds that are holding those atoms in place with each other or those molecules in place. Depending on the type of bond, will change the amount of energy that's stored inside of it, as well as what atoms are involved will change the amount of energy. Some other types of forms of energy are things like electrical, which is related to the flow of those electrons, light or radiant energy, which is associated with those energy transitions inside of the atom, and then nuclear energy, which is the energy that's stored inside of just the nucleus of the atom. And that's kind of where we get energy when we have like a nuclear reaction. And so that can be either through the decay or through fission of the nuclear process or through fusion when we create new nuclei as well. So in the same way we had the law of conservation of mass, we also have the law of conservation of energy. And that means that our energy can't be created or destroyed. It's only converted. So when energy is transferred between objects, we convert one energy from one form to another. And our total amount of energy is going to be equal. So in this example that she's showing here, she's taking that energy of that bowling ball, she's pushing it down onto that spring. So she's providing energy to that ball. As that coil gets pushed down and down, it's kind of storing that energy as a potential energy. And then when she lets go, that potential energy gets converted into kinetic energy as it shoots the bowling ball up. Probably a dangerous experiment for her to do, standing right there. And so one of the more common ways that we see this energy transferred is in the form of heat. And so heat happens anytime objects are not at the same temperature. And it flows in the same direction. It always flows from a higher temperature object to a lower temperature. So when we talk about our flow of energy, we're going to use terms like system and surroundings. So system is going to be what we are interested in. Surroundings is going to be everything else outside of that. So in this case, our system is this orange box and our surroundings is anything else. And so we're looking at what happens when the system has a higher temperature than its surroundings. So we should think about which direction that heat's going to flow. And so the heat should flow from the system to the surroundings. And so the heat of the system, that Q, is going to be negative. It's going to be losing energy. And the term we have for that, when a chemical reaction is losing energy as it goes forward, is exothermic. It means that it's releasing energy as it goes through that process. So the system is losing that energy and it's giving it to its surrounding. Sometimes people get a little bit confused about that because they think about it in terms of the surroundings. The Q for the surroundings is going up, which means that it's becoming higher, which would be a positive change. But when we're describing this part, we're really focusing on what's happening to the system, not to the surroundings, which is why the heat of the system is going to be negative. Let's look at another example. Let's say that in this case, our system is cooler than our surroundings. Well, this time then the heat from our surroundings should flow into our system. Similar to like if you have a cup of ice, your air is your surroundings and it's warmer than your system. So it's going to flow heat into your system. So the heat of the system is going to go up, it becomes positive, and it's what we call an endothermic process because it's taking in that heat. So system is defined as the material or process with which we're studying the energy changes within. Surroundings is everything else outside of that. And these are all things that your system can exchange energy with. And so we're always looking at the exchange of energy between the system and the surroundings, whether that's before the energy transfer to after. What happens from the system gets found in the surroundings. What happens in the surroundings comes from the system, right? So there's a balance there because none of that energy is just going away. We have to account for it. Now, for the units of energy, we were talking about energy before as being associated with our kinetic energy, which is 1/2 the mass times the velocity squared. So the units of energy, a common one is a mass is in kilograms. And if our velocity was in meters per second, then we get this unit here, kilograms times meters squared divided by second squared. Now that's kind of a handful to write out. And so that can get simplified into this term joule. And so this is the basis of what a joule is, and a joule is typically how we talk about our energy. And so it's the amount of energy needed to move 1 kilogram of mass at a speed of 1 meter squared, or 1 meter per second for its velocity, which can be quite a lot. So we're going to use joule often when we talk about the energy of a system. On the other side, we can also use the term calorie. Now, calorie is related a little bit more for heat, and it's because it's the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So when we talk about calories inside of your food, the basis of that calorie was related to this idea about the amount of energy needed to raise 1 gram of water 1 degree Celsius. And so down here is a conversion factor between calorie and joules. So 1 calorie is 4.184 joules. Now, just like any of our other units, we can use those prefixes in front of them. So we can put in a small k in front of that j, and that becomes kilojoules. And so 1 kilojoule is 1,000 joules. And kilojoules are often used when we talk about energies of systems because it's in the right realm of a lot of our energy transfers that we'll see. You could also do a small m, 1 millijoules, and that would be 0.001 joules, a lot smaller than a joule. And so we can use a lot of different prefixes there. Calories can do the same thing, where we can put a K in front of it and it can become a kilocalorie. We could put an M in front of it, become a millicalorie, right? And so all those prefixes, the reason why we needed to memorize them is because we can still be using them for a variety of things. Now, before we go any further, I do want to clarify one thing, and that's that when we talk about calories for food, it's different than calories for chemistry. Because of one thing, and that's what you want to look for, is this capital C. So food calories are a capital C, and one food calorie is actually the same as us saying 1,000 normal calories. So a food calorie is really kilocalories. I don't know why they did it, but that's the way that we've started to label things, and it's probably because it seems nicer when you eat 200 calories of something instead of like 200,000 calories of something. And so a food calorie will have that capital C, and it's going to mean 1,000 normal calories. So a bag of chocolate candy has 220 calories. How much energy is that in kilojoules? So we have 220 calories, and that's with a big C. So that means that that's a kcal. So if we want to convert that over into joules, then we know that 1 calorie is 4,184 joules. And so I'm using this conversion here. Or what you can do is you could say, well, 1 big C calorie is 1,000 small calories. And 1 small calorie is 4.184 joules. Good. Almost there. One last part. We need to get that kilojoules. So 1 kilojoule is 1,000 joules. And then we just need to plug it in. We can do that number crunch. And so we're going to find out that this becomes 920 kilojoules. And so our answer is going to be A. So we can use it just like we've done all of our other unit conversions. Now, from there, what we're going to start to study is thermodynamics, which is the study of the energy and its conversions inside of these different processes. And so the first law of thermodynamics is that law of conservation of energy that we've been talking about. And that means that the total amount of energy in the universe is constant. Whatever happens, we're not creating more energy, we're not losing more energy, we're only transferring it. So we can never design a system that just keeps producing energy. It's only ever converting that energy, and so there's always got to be more energy coming in as it comes out. That's the idea of like a perpetual motion device, right? Is that it never actually works because at some point we have to have other energy coming in, keep it going. So the conservation of energy requires that the sum of the energy changes in the system and the surroundings is 0. And so the idea behind that is that anything that we put in for the system, we find in the surroundings. Anything that got taken from your surroundings ended up in your system. And so this delta sign is used often in thermodynamics because it's the symbol that means change. So the change of the energy of the universe is 0. We don't create any, we don't lose any. And the reason why we use the change sign is because that's going to be the final amount minus your initial amount. And so that change in the energy of the system plus the change in the energy of the surroundings is always equal to 0. The second part is your internal energy. So the internal energy of a system is related to 2 parts. It's the sum of its kinetic energy. It's also the sum of all of its potential energy. So what it could do inside. So it's the energy that it has as it's moving around, and it's the energy that it has stored inside of it. The change in the internal energy of a system depends on the amount of energy in the system at the beginning and at the end. It doesn't matter in the middle. What that means is that it's what we call a state function. And so state functions can be really useful, but sometimes they can be a little bit confusing. So state functions, what you want to think about is that it doesn't matter the pathway that you took. It only matters where you started and where you ended up. And so it's this idea that it's always your final position minus your initial position, and that's going to be your change overall. It doesn't matter how you got there. And the reason why that's helpful for us is for a chemical reaction, then that would be our energy of our products minus our energy of our reactants. So let's talk about state functions first, and then we'll talk a little bit about how that works with our system. So an example of a state function is kind of us walking to the top of a mountain. So as we walk to the top of a mountain, we have two options. We can take a long and winding path, path A, which takes about 12 miles. But it'll get us from the bottom of the mountain, 0 feet, up to the very top, 10,000 feet. On the other hand, we have a short path, but a steep one, path B. It only takes us 5 miles to walk it, but it's a very steep path instead. And so when we're looking at this, a state function means that it doesn't matter whether you took path A or path B, your value is going to be the same. And so an example of a state function would be the difference in elevation that you went through. Whether you took path A or path B, you always started at 0 feet and you always ended up at 10,000 feet. So your change in elevation was always 10,000, no matter which path you took. So that's an example of a state function. Now, if you said the distance that you walked, the distance would not be a state function. And that's because if you took path A, you walked 12 miles. Your distance that you covered was a lot more. If you took path B, then you only walked 5, and so your distance was different. So some things do depend on the pathway that you take, and some things don't. And so that's how you classify things as being either state functions or non-state functions. It doesn't, whether it depends on the path you took or whether it is independent of the path that you took. And so for our energy changes, sometimes what we do to help us visualize what's going on is we draw out these energy diagrams. And so these energy diagrams can be a representation of the pathway that you're taking. And we can see which parts stay the same and which parts don't stay the same as you go through that pathway. So in this example, what we're showing is kind of this conversion of our reactants to our products. So we're taking carbon and oxygen gas, and we're converting that into CO2. And so we're looking at their internal energies, how much energy is inside that product. And so our carbon dioxide has lower energy than our carbon and our oxygen, so we can put that at a lower level. Our carbon and our oxygen gas, they start off at a higher level. And so when we imagine going from our reactants to our products, we're really dropping down in energy. That change in that energy is going to be negative because we're moving from somewhere where they had more energy inside of them to somewhere where they had less. And so you can kind of visually see there's a drop down in that change. On the other hand, if we have the opposite process, we're taking that carbon dioxide and we're converting it back into carbon and oxygen gas, the internal energy is then going to go up because we're traveling from this lower point to the higher point. So when we're looking at energy changes, we're looking at where that internal energy is being stored. Is there more energy in the products? In which case, more energy in the products, in which case you're having a positive change, or was there more energy in the reactants, in which case we have a negative exchange. So the total amount of internal energy in 1 mole of carbon and 1 mole of oxygen is greater than the internal energy in 1 mole of CO2. So when we're going through that reaction, there's going to be a release of that energy. So our reaction is losing energy, and so it's giving that away to the surroundings. Whereas in the opposite, when we're going from the CO2 to that carbon and the oxygen, then the surroundings are going to end up absorbing energy, and so there's going to be a positive change for it. Sorry, a positive change for the reaction. Just to clarify that. So when you're setting up these equations, just remember that the minus of your delta E of your system is equal to the change in that of your surroundings, or vice versa, which is the change in your system is equal to the negative change of your surroundings. They actually both mean the same thing. And we get this because 0, which is our energy change of our universe, is equal to the change in the energy of our system plus the change in your energy of your surroundings. So what you're really looking at in this is that no matter what happens, the change in the energy of that system, whatever value we get, whether that's negative 100 or positive 450, the surroundings are going to feel an equal amount of that change, but it's just going to be the opposite sign. So surroundings would have gained 100. So let's say that these are joules. Would have gained 100 joules because the system lost 100 joules. If our system gained 450 joules, well, that came from our surroundings. So our surroundings lost 450 joules. So it's kind of what we call a zero-sum game, in that those two values, what you gain from your system and what you gain from your surroundings, they have to be equal to 0. Now, how they exchange this energy is going to be in 2 forms. It's going to be either through their heat or through their work. So a positive Q means that whether that's your system or your surroundings, gained heat or thermal energy. A negative Q means that they're losing thermal energy and they're getting cooler. Work, on the other hand, a positive work means that there's work done on the system. So that's going to be work is being applied, whereas a negative means that work is done by the system. So that means that it's doing the work on something else. So work seems to be where people struggle a little bit with signs, because you have to really think about, well, is my system doing that work or is work being done onto it? And so this is how they do that exchange from your system to your surroundings and from your surroundings to your system, is through either our heat or that work. And so that's what we're going to focus on for this chapter, is we're only going to look at heat and work exchanges. So let's look at how much energy, internal energy, changes for a system that does 422 joules of work and loses negative 227 joules of energy. So it does 422 joules of work, so that means that that work value is negative 422 joules because it does it. It then loses heat. So it loses 227 joules of heat. So our change in our energy should be our Q plus our W. So it should be negative 227 joules plus negative 422 joules. And so our energy change becomes negative 649 joules. So the hardest part about this was trying to figure out what our signs meant, and making sure that we get those to align. And so you just want to make sure that you're reading carefully about the wording. So did we do the work, or was work done onto us? Did we lose the heat, or did we gain that heat? And so how this works in real life is that sometimes when things are moving around, your energy is converted into both your kinetic energy as well as your heat energy, and things can be transferred. So let's take let's take a pool table as an example. When we roll that ball, some of that energy gets converted to heat by the friction of the felt. That's why when you hit the ball, it doesn't just roll on forever. Okay? Over time, that friction saps away some of that energy. And so when we first hit the white ball, we're giving it some amount of kinetic energy. Let's say that we're giving it the 5 joules of kinetic energy. We lose some of that energy to the friction, and then when it collides with that purple ball, we could say that we transferred the rest over. So if we wanted to look at that exchange of that system, the total energy, that delta E, is going to be our final energy of that white ball. So it ends up not having any kinetic energy because it stopped moving, so 0. And its initial was 5.0 joules, and so its change is going to be negative 5.0 joules. The kinetic energy of the purple ball, well, it started off at 0 joules. It ended up going 4.5 joules at the end, and so its delta E is 4.5 joules. So pick that up. So when we're looking at that white ball and we're trying to figure out, well, how did all of its energy go away? It lost that energy in kind of 2 ways. It lost it by transferring the energy to our purple ball, making it move. And so we can classify that as our work. Or it lost it as it turned into heat from that friction, which we can classify as its Q. So its work ends up being negative 4.5 joules because it applied that to that purple ball. Our Q is going to be 0.5 joules, and that should be negative because it lost that to friction. And so you can see that our delta E, it all ends up being accounted for, that negative 5.0 joules. And so I'm getting these values from this diagram here, in when it tells us how much was lost and versus how much we gained in their purple ball. Now on a rougher table, then the kinetic energy, we lose more of it to friction, and so less is transferred to the purple ball. So on a rough table, we still lose the same amount of energy, still 5 joules because that's all that it had, but this time 3 joules of it was lost to heat. So our delta E, I have these values flipped, this should be a 2, this one should be a 3. 3 joules was lost as heat, and only 2 joules make it as our work. So in both of those examples, we can see that our energy is being accounted for. We're either losing it through that work or we're losing it through that heat. So that delta E change is a state function. It really doesn't depend on whether we lost it through heat or work. Each time that delta E ended up being the same. It didn't depend on the pathway. It just depended on that it had 5 joules to begin with, and it had no joules at the end. It didn't care whether we lost that through work or heat. But work and heat, they cared whether it was on a smooth table or a rough table. So Q is a non-state function, and W is a non-state function. They depend on your pathway. Whereas our delta E didn't. Now, work that we're going to talk about for our class is what we're going to call pressure volume work. And so it's done by the volume change against an external pressure of a system, or a pressure change at a constant volume. But it's this idea that when we see this primarily with gases for chemistry, but it's when gases expand, then the delta V has to be adjusted, the volume that it takes up. But since it's done at room temperature or at atmospheric pressure, then there's some force being applied to that gas. For them to take up more volume, then they have to push back that gas and make space for them. So you can kind of imagine them being the piston. And so for them to take in more volume, they ought to push that piston up to make that space. And so that requires some energy, and that is our work. So our work is kind of this constant pressure times the change in that volume. And so that uses a conversion of 101.3 joules to move 1 atmosphere of pressure back 1 liter. So how much work is done when a container expands 2.55 liters against an external pressure of 1.50 atmospheres? So we know that the work is the negative part of that pressure, 1.50 atmospheres, against the change in the volume. So now we are expanded, so that should be a positive change. So that delta V is 2.55 liters. And then it expanded, so it's a positive change, so it's plus 2.55 liters. So our work becomes 1.50 times 2.55. And so that becomes negative 387 joules. Now, if we would think about this, we could double check that it's negative. Oh, sorry, not joules. Skipped ahead there. We didn't even do our conversion. So 1.5 times 2.55, this became 3.825 liter atmospheres. And then we want to get that into joules because our units are in joules. So we need to take that negative 3.825 times that by 101.3 joules is 1 liter atmospheres. And so now we get negative 387 joules. One way to double check that your signs are correct is think about, well, if we are expanding in our volume, should that take work or does that give us work? Right? And so when you think about being a piston, it's kind of like you have this certain amount of pressure crushing you. And so if you want to take more space, then you got to raise that weight, that piston up to make that space for you. So that takes work. If you're getting crushed by the piston, then that doesn't actually take any work, right? So say you're holding it up and you get tired of holding it and you let go, your volume is going to get smaller, but it doesn't take any work from you. You end up actually gaining some work back as you go down in your volume. Right? So think about that when you think about whether your W should be positive or negative. It's always a good idea to check it at the end. It's easy to make a mistake with the signs. So you always want to be double checking. So thermochemistry is specifically just the study of heat changes for those chemical reactions. So thermodynamics kind of looks at all of it involved. Thermochemistry only focuses on the heat. And so a closed energy system means that there's no exchange in there. Whereas an open energy means that we can have mass and energy moving back and forth between them. So heat is what we're looking for, that energy exchange just through its temperature, or through its thermal energy. And it always happens between your systems and surroundings, but they have to have a difference in temperature. So they're always kind of moving until they have the same temperature. Temperature is the measure of that thermal energy change within a sample. Now, heat flows from a high object temperature to a low temperature one until they both reach the same. When they reach the same, there's a term for that. It's called thermal equilibrium, but it means that they're in balance. So two objects that are at the same temperature, we can't get them to exchange any more thermal energy because as they lose it, the other one gains it, and then it sends it right back. So there's a balance there. We won't see any net change overall. So when the system absorbs heat, its temperature is going to increase. And that's going to be directly proportional to the amount of heat changed. Now, some materials, the change in the temperature happens very quickly for the amount of heat we put in. For other materials, it takes a lot of heat for it to feel a change in that temperature. And that's related to a new term called heat capacity, which we use this big C to stand for. Now, heat capacity depends a lot on that object, the material it's made of, and also how much of that material. So the units for heat capacity are joules per degree Celsius or joules per Kelvin. So it's the energy it takes for it to go up 1 degree Celsius or the energy it takes for it to go up 1 Kelvin. So an idea is going to be like if you pour water, boiling water, into a glass cup, the glass gets hot pretty quickly, so it has a low heat capacity. Whereas if you pour it into a mug, your mug doesn't get as hot, and so it's got a longer heat capacity, or a higher heat capacity. And so our heat capacity is kind of that relationship between the amount of heat that it takes and the temperature change that we see. So the larger the heat capacity, then the smaller the temperature rise for that same amount of heat. Now, from there, we can also get a little bit more specific. We can introduce something that's called the specific heat of that material. And so what we're doing is we're separating away the mass of that material versus the heat capacity of it. So just one heat capacity kind of combines all of that into one thing, where it's using just that total mass, that total material. It's saying all of that's all accounted for, and so it's just the heat times the change in that temperature. Specific heat capacity breaks it down a little bit more, and so now we have to have the mass of that object because specific heat capacity is in joules per gram per degree Celsius. So specific heat capacity is kind of an intrinsic value. So it has to do with the material that we use. And so you can see that metals have really low specific heat capacities. This is why they're used so well for things like cooking, because when you heat that pan, you don't have to put as much energy inside of it in order to get it up to a high temperature. Other ones, like water, has a really high specific heat capacity, which means it requires a lot of energy for it to go up in its temperature. And so this is why boiling water takes so long, is that it needs a lot of energy inside of it. It has to keep putting energy in and in and in for us to store that energy so we can raise the temperature. So the specific heat capacity, we use that for a material, and you can always tell a specific heat capacity from just heat capacity based on its units, joules per grams degree Celsius. It's also normally written as this C with a lower s. So I like to think of our Q as what we call MCAT. So Q is equal to your mass times your specific heat capacity times the change in your temperature, which is where that cat comes from. Just remember that delta T is always going to be your final minus your initial. And this becomes important because if you get them flipped, then you're going to think that you lost heat when you actually gained heat, or you're going to think that you gained heat when you lost heat. There's one last type of heat capacity that sometimes gets used, and it's called the molar heat capacity. And so it's the amount of energy required to raise 1 mole of a substance 1 degree Celsius. It doesn't get used as often when we talk about it in terms of our calorimetry experiments, but we do see this used much more often when we're dealing with chemical reactions. So when we're looking at the heat capacity of the reactants or the products, then sometimes we see molar heat capacity start to get used. So we know that heat transfer occurs when two objects are placed in contact. The heat flows from one material to a lower one. And we know that the heat flow stops when they both reach the same temperature. And so the amount of heat energy lost by the hot material ends up being equal to that gained by the cold material. And this principle is what calorimetry is all based on. So calorimetry is going to be one way for us to measure the amount of heat inside of an object by looking at how much it releases to its surroundings. So a block of metal at 55 degrees Celsius is added to water at 25 degrees Celsius. Now, it should lose energy to that water. So the Q that the metal loses should be equal to the Q of the water, just the opposite sign of it. And so if we know the mass of the metal, if we know the specific heat capacity of the metal, and we know the temperature change of that metal, then we can start to look for that heat change of the water. And so if we know two of these, we can find our third. Now, most often, what we're going to do is you'll know the mass of the water that you're put in. You know the heat capacity of water, because that you can get from a table, and you're going to measure its temperature change. Now, you're going to know that metal that you put in, its temperature, what it started with, and so we'll know where it ends up, and we'll know its mass. And so we're going to use this technique to find the heat capacity in a lot of cases of the metal, because once we know the heat capacity of the metal, then we can start to identify them based on the different rules. Just like what we did with density, right? We can compare it against a table, and we can match up its heat capacities to a few of the options. So overall, we know that the exchange of heat energy, that's going to take on this equation here. Q is our mass times our specific heat capacity and our delta T. Work, on the other hand, work takes on a different look. Work was related to that change in that volume against an external pressure. So our delta E, that internal energy, is always going to be that Q plus that W, but now we have two equations that we use back to look at those exchanges that are happening, whether that's the Q or whether that's the W. Now, what we're going to focus on for the rest of the lecture is a little bit on this calorimetry side of things. So calorimetry is when we have an isolated system. So we're going to try to put our system into a device, and we're going to try to measure the heat change that the device feels for its surroundings. So the surrounding area is what we call the bomb calorimeter. It's basically the device that's going to capture all of that energy. And so it's going to end up taking in the energy that we lose or gain from the system. And so it's a way for us to measure the energy released through different chemical reactions, which are a system, or through different materials as they go through a change. And so we keep it at a constant volume, because if it's at a constant volume, then that energy change can only be happening from that Q, because this work because the constant volume is there, is zero. So delta V becomes zero. And so this work term all becomes zero and ends up going away. And so we're going to use this to introduce a new term, and it's called enthalpy. And so enthalpy is a state function. And what it does is it looks at the energy of a system plus the pressure times its volume. Now, this is how we're going to try to adjust what's going on to no longer be talking about the heat, but be talking about the enthalpy, because our enthalpy at a constant pressure ends up being equal to the heat. Heat depends on whether you, what pathway you take, whereas enthalpy doesn't, because it's just the amount of heat that's evolved over time for that entire reaction, right? Or the heat that's taken in over time over the entire reaction at constant pressure. So delta H and delta E are actually ending up being very similar. Delta H is just H and delta E is Q. And so as long as our volume changes are 0, then basically H becomes delta E. But when we have a lot of gas that gets produced, then our volumes change a lot. And so then we start to see a lot of deviation between enthalpy and heat, or enthalpy and our internal energy. But we just want to use enthalpy because we want to start to be able to look at our reactions. And so as long as we're at this constant pressure and this constant volume, then we can find the enthalpy of that reaction by looking at the heat of the reaction, which is where we use our calorimeters. And so let's try one of those heat exchanges. We're jumping over to slide 72. And so a 75-gram piece of lead is initially placed in 125 grams of water, and the piece of lead was at 435 degrees Celsius. The water was initially at 23.0 degrees Celsius. What is the final temperature of the mixture? So in this case, we've taken that lead, it has some mass, it has some temperature, and we know its specific heat capacity here. We're putting it inside of that water. That water has a mass, it has a temperature, and we also know the specific heat capacity of water. Now water in this case is 4.184 joules per grams degrees Celsius. That one is actually so common that I've gone ahead and I've given it to you on the back of your equation sheet because we'll use water so often for our calorimetry. So if we want to set this up, we know that the heat that's being lost by the water is equal to the heat, or sorry, the heat being gained by the water is equal to the heat that's being lost by the lead. So we want to start to plug in our Q equals MCAT. So the mass of the water times the specific heat capacity of the water times the temperature of the water is going to be equal to the negative for the mass of our lead, the heat capacity of our lead, and the temperature of our lead, or the change of temperature in our lead. So we have our equation. And so now we just need to start plugging in our pieces. We know that our water was 125.0 grams. We know its heat capacity is 4.184 joules per grams degrees Celsius. And then our delta T. Well, we don't know what our delta T is. We know that its initial temperature was 23.0 degrees Celsius, but we don't know what its final temperature is. That's okay. We can leave that there for now. When we get to our lead, we want to make sure that we put in that negative sign because they should be the same value, but opposite signs because one is gaining it and one is losing it. Now the mass of that lead is going to be 75.0 grams. Its heat capacity is going to be 0.130 joules per grams degrees Celsius. And its final temperature, we don't know, but we do know that it started at 435 degrees Celsius. So if you imagine this, one object is starting at a high temperature here, and it's going to drop down to our final temperature. The other one is starting from its lower temperature, 23, and it's going to move some amount to get to that final temperature. So they're both going to end up being the same final temperature, but what we don't know is where that is. Because it depends on your masses and it depends on your heat capacities. If you have a big change in either one, then one side will move a lot more than the other. We can't just meet in the middle. So let's go ahead and simplify some of this down. So I'm going to take the 125 and multiply that by 4.184. And so this tells me that our water has a heat capacity of joules per degree Celsius of that. And our lead, 75.0 times 0.130, is at 9.75 joules. And so we've consolidated these, and so now we have TF minus 435 degrees Celsius. And so what we want to do now is we want to try to get rid of these terms. And so I'm going to go ahead and I'm going to try to distribute this 523 to its final temperature and then its initial one. And so I'm going to spread that out for each of them. So what that means is I'm going to take 523, I'm going to multiply that by its final temperature. And so we're going to get something. I'm going to make this a little bit smaller so we can fit it in there. This becomes 523 times its final temperature minus 23 times 523, 12,029 degrees Celsius. On this side, I'm taking that 9.75 times its final temperature minus, so this is really negative 9.75. 9.75 times 435. 4,241.25. So that's going to become positive. And that's because we have a negative 9.75 times a negative 435. So that's why it's the positive. And so I'm going to try to consolidate these forms. So 523 plus 9.75, all of that becomes 532.75. That's my final, times my final temperature, equals, and then I take the 4,241.25, and I add to it the 12,029. I divide that by 532.75. And so we're going to get that as its final temperature of 30.54 degrees Celsius. And so that's going to be the final temperature. So we're going to stop there for the lecture. And then what we're going to do is we're going to do some problem solving, and we're going to do that in a separate video afterwards. All right, good luck.